Hey, APCalc class, so we're going to continue on with our notes in section 4.4, and we ended on we finished example 4, and I'm going to start with example 5. And in this problem, this is a very typical type of AP type question that you might see. So they're going to give you a function that represents a rate. Okay, so it says oil is leaking from a storage tank at a rate, they're calling it R of t, and so it's negative t squared over 12 plus 100 gallons per day. So it's a quadratic equation. It's just a parabola that opens downward, so it's just a section of that, and it has a real small a value, so it's curving very slowly downward. Okay, so I sketched out this graph. I'd also enter it in a calculator, so just to show you, I would enter that equation in. This would very likely be a calculator type question. So I've put it in here, and on this Calculator Pro app, you have to, so it looks like 1 divided by 12, and put the negative there, x squared plus 100. And then when you set up your window to set it up to what we're looking at, I went from 0 to 20 for my x min, x max, and then 0 to 200 on the y min and y max scale, and I counted by tens there. So if we look at that graph, it looks kind of like what we're seeing on our page. Okay, so I've got that. I sketched it out, approximate. I got these values. It was 100 when you put in 0. I think this was like 66 or something like that. So I sketched that out just approximately. Okay, now, so we graph that out, and then for part B it says how much oil has leaked out by the end of the 5th day. Okay, so we're starting at day 0 and we're going to day 5. So really what that's asking us to find is after 1, 2, 3, 4, 5. So after 5 days, so I must, oops, let me undo that. Didn't mean to pull that down. After 5 days, so right in there. Okay, so it's, what they give us is a rate, okay, and then the time on our x-axis is days. So it's gallons per day. And then if I'm going to find this area, really what I'm multiplying is gallons per day times days, which is going to leave me with just gallons. It's going to give me so the area underneath here represents the total amount of gallons that have leaked out. And that's from starting at day 0 to day 5. So this area that I've shaded, when I integrate this function, that's really what I'm finding. I'm finding this area, which is gallons per day times days. It's going to leave me with total gallons. Okay, so what I set up is just the antiderivative from 0 to 5 of this rate function. So when I integrate, a common phrase that they use is when you integrate, you lose the rate. So the rate being per day, so now it's just going to be gallons. When I integrate gallons per day, it leaves me with gallons. Okay. So this one, I could do it on my calculator, and I'll show you that too, but it's not that difficult to do this one by hand because, if our exponent is 2, so we add 1 to 2 and get 3, and then if we divide by 3 or times by 1/3, that's going to change this to negative 1/36 instead of 1/12, and then it's t to the third, and then with my constant I just have plus 100t, and if I'm going from 0 to 5, then I'm just going to plug the 5 in there, 5 cubed times negative 136 plus 100 times 5, and I probably just enter that in my calculator, and then when I put the 0 in there, those both become 0, so I'm subtracting 0 when I use my fundamental theorem of calculus. Okay, and so that gives me 496.528. Okay, so we always want to go 3 decimal places when you give an answer on these type of application questions. On the AP exam, you always got to go 3 decimal places. Okay, so that's how that one's going to look. And then this next one, a similar question, but this time just a different interval. It says, how much oil has leaked out between the 5th and the 10th day? So, i.e. on the interval from 5 to 10. So we're just doing the same process. Now, if you were doing this and this was a calculator problem on the AP exam, what I would recommend is, instead of always rewriting this formula out, because if you accidentally didn't write the minus sign or you made a mistake writing it, you're going to get dinged on that. So if it's something where you don't have to do the work, and I think something like this would be a calculator style question, just write R of t. If they're calling it R of t, then just write the integral of R of t dt, and then we're going to go to our calculator and we're just going to put that in. Now we already had it entered in because we graphed it, so it's right here in y equals. So if I go back to the home screen and if I hit math, so if I use the math button, and item choice number 9 it says function integration, so you just choose number 9, and then you can enter in from 5 on my bottom bound up to 10, And then in here, instead of retyping that, since we already have it in y equals, use that alpha f4 and choose number 1 for that function. And then we just we can hit enter after that, and we come up with 475.694. Okay, and that's what I had when I calculated that before. Okay, so now we're just working on the area. Let me sketch that from here to here. Oops. So is this area? I'll do that in a different color maybe. So now we're looking at this area right here. Okay, so still a 5-day period, but a little different part of the curve, right? Okay, so now next question, what is the average daily loss of oil that is leaked out over these 20 days? Okay, so average daily loss, that's an indication. We studied average value. They want you to find the average value for that. Okay, and if you think about it, if you take, if I go from 0 to 20 days and I find the total amount of gallons lost there, so if I do the whole area under there, that's the total gallons lost over the 20 days. But then if I divide that by 20, that's going to give me the average amount lost per day. So that's the same idea, average value. So it would be, that formula is 1 over b minus a, which would be your 1/20th, and then times the integral from 0 to 20 of that function. Okay, so we can do that one on our calculator too. So we would have, so again, math 9, and this time we're going to go 0 to 20, 0 to 20, and here I've still got my alpha f4, that's my function. Choose that one. I'm going to hit enter here, and then I'll divide that answer by 20. So I hit enter. Is it still thinking? Sometimes it takes a little while for it to think. It takes a minute to calculate that. And then I'm going to divide that by 20. So I'm just going to hit divided by 20, enter. And so then I get 88.88, repeating it looks like. So 88.8889, and you can either round or truncate. So I rounded up, I guess, 88.889. Okay, gallons per day. Because again, I'm dividing. So this was just gallons, but this is divided by 20 days. So it puts it back as a rate. It's my average daily rate, right? Average daily loss. All right. So hopefully that makes sense. Okay. So we've been working with the first fundamental theorem of calculus. This is the second fundamental theorem of calculus. And kind of the main idea of this one, it's kind of based on the idea that the integral and the derivative are inverse functions of one another, okay? And so the idea here is that in the second fundamental theorem, if I'm taking a derivative of an integral, okay, what happens here is that basically they cancel each other out, and it just leaves you with whatever that function is, okay? Now in here, and you have to have some bounds, right? You have to have, in this, you're going to have a constant as the bottom bound. And in this, usually what you're going to have on the top is x or some variable, because it's usually a function in terms of x. Now here, because they don't want to have an x in here as well, they usually call it a function of t. And usually in applications, the function is in terms of time, so that's why they're using t here. Okay, and so what happens is when you integrate this piece and then take the, and then it's a definite integral, x gets put into that when you do f of b minus f of a. Now it's in x's, and then I do derivative of that in terms of x, and I get f of x. Okay, so that's why the f of t changes to f of x, because the top bound is in terms of x. Okay, so in simplest maybe language, the derivative of a definite integral is the original function with the variable replaced with that one. So yeah, basically it's the original function. It cancels out, and then you just replace the variable with whatever that top variable is. Okay. Okay, so let's take a look at a few examples here where we're using that second fundamental theorem of calculus. So on the first one, we've got a derivative of, looks like x, or a derivative of from 0 to x of t squared plus 1. And so again, all you're doing, and I could show, we could actually work this one out just to show why it works the way that it does. So if I was doing, pin disappeared, if I was doing the derivative of this integral. So let's do the integral, because this isn't that hard to do. So t cubed over 3, and then plus t, right? And then if I was doing that from 0 to x, because those were the bounds on there, right? And that means that I would replace, I'd go in here and I'd say, okay, now I'm still doing the derivative of after I simplify this. So I would have x cubed over 3 plus x, and then minus 0, because I have a 0 on the bottom bound, so I just have that. And now if I do the derivative of that, right, if I do the derivative of x cubed over 3, well, that just changes back to x squared, and the derivative of x is 1, and so I just end up with x squared plus 1, right? And that's exactly what, you know, kind of the rule says. You just, it's the original function, but you replace the variable with whatever you have up there, okay? So here's another one, and you know, we could do this and show the work again on it if we want to, and then maybe after that, then we just say, okay, this works, and we don't have to actually do the integral and then do the derivative, because sometimes these expressions are too complicated to do that anyways. But on some of these simpler ones, we can demonstrate that this is true, that when, you know, we take the derivative of the integral, they cancel each other out, and then the variable up here gets replaced as long as I have a constant on the bottom and just like that x, a different variable on top. So dx of, now when I do this integral here, I'm going to get 5/2 t squared minus 3t, and I'm going to evaluate that from 2 to x, right? Double like this. And so when I do that, I've got derivative, and so then I put this in, it's going to be 5/2 x squared minus 3x, and then I'm going to minus, and it's going to be 5/2, and then it's going to be times 2 squared minus 3 times 2, right? Okay, so when I simplify this, what's going to happen here? I'm going to have, so this would be, and now keep in mind now, do I need to, could I simplify all this? Yes, I could, but keep in mind that whatever I get inside of here, it's just a constant, right? So when I take the derivative of all this stuff, this is a constant. It's just going to disappear. So I could spend time simplifying it, or I could just say, well, whatever, it's, when I take its derivative, it's going to become 0. So I think that's what I'm going to do. So now when I take the derivative of 5/2 x squared, I know that multiply that out, I'm just going to get 5x. And when I take derivative of minus 3x, I get minus 3. And all this stuff, which is a constant, is just going to be 0. So hopefully that demonstrates when you have a constant on the bottom, x on the top, you know, this rule that we stated up here, it's just the original function with the variable replaced, and we see that that's the case on both. Okay. There are a couple extra rules here. When you do have something other than just x on top, there's a chain rule that gets involved. So you still are just going to replace with whatever you have up here. Like if it were x squared, you'd replace, you know, with the t with x squared or something. But then you have to multiply it, because we're doing a derivative. There's a chain rule, so then you multiply by g prime of x, whatever, you know, they're calling g of x the top bound. So if it's something other than just x, you know, then we have to apply a chain rule there, because that's what we do with derivatives, right? Now, if we do have a derivative on both top and bottom, it's not a constant there, then when we subtract, it's not going to, you know, we're still going to have another expression there, because it's not just a constant here, like what we had here. When we had a constant on the bottom, then we subtracted a constant, and then we did the derivative of that, it disappeared, right? So that's not going to happen here. So we're going to have some expressions left right here. So we have to put in the top bound number first, you know, replace any t's with whatever that top function is, and then subtract, and then we're going to replace the t's with whatever the bottom function is, and then apply the chain rule in each. Okay, so let's take a look here if we can maybe make this make sense with some of these. So here I've got a constant on the bottom, and then I've got like a g of x, some other function on top. So that would be like this first rule right here. So let's just see if we can apply this first rule. So I'm gonna say it's so instead of t here, I'm gonna have 5x squared plus 1, but then I have to apply that chain rule right here. I have to multiply by the derivative of that top function, which is 5x squared. So I'm going to multiply this times 10x. That's how I would, you know, get that solution. So 50x cubed plus 10x for that one. Okay. And on the next one, now this would be kind of, so this was this rule for part A, and I think for part B, because we have we have a function here and one on the bottom, it's not a constant on the bottom, then we'll have to apply this rule right here, this second rule. Okay, so again, just replace. So 3 times t becomes 3 times 2x cubed plus 1. And then we have to do a chain rule there, which means we have to multiply that by 6x squared, which is the derivative of that 2x cubed, 6x squared. And then minus, now because we have a constant, or not a constant, we have a variable there, or another function. So now we replace, so now it's going to be minus 3x plus 1. And the chain rule in this case doesn't really matter, because when I do the derivative of that x, that would just be, technically it would just be times 1. The derivative of x there is just be times 1. Okay, so then we just simplify this up. So I'd have 6x to the third plus 1 times 6x squared minus 3x and minus 1. And so I could simplify this a little bit more. I'd have 36x to the fifth plus 6x squared minus 3x minus 1. Okay, so that would be how I would apply these two rules to the situation we have right there. Okay. Okay, example 8. So in this one, I haven't seen many examples or many problems on the AP exam where they actually ask you to use a regression equation, but I mean, you could. You've done this in algebra where you just, in the L1 and L2 function on your calculator, you'd enter all these values and then you'd enter all these in L2. And if they asked you to use, I think it said to use cubic regression, yeah. Use a cubic regression, you could do a cubic regression and it would spit out these numbers. Now, I just left this written out because I'll talk about this problem, but I don't see this as probably a problem that you're going to get on an AP exam. And plus these numbers get they're such small decimals and kind of weird to work with. But the idea is that, okay, so let's just say that this information, time and velocity, okay, so we can model that with this function right here, which is going to be, we input time and then we output a velocity, right? So this is something to find velocity, which would be like a rate of change, right? And now they say use the fundamental theorem of calculus to approximate the total distance traveled by the vehicle in this test run. So since the test run goes from 0 to 60 seconds, right? And this is a rate. This finds speed, right, or velocity. Okay. Then again, so what we do is if we integrate something that's a rate, that gives us the area under it, which is just going to be that distance, and that's what we're looking for, is that the total distance. Now in this case, I think it says that it is. I guess it didn't say that it's always moving. Well, we're going to talk about the distance the difference between total distance and displacement, but I think on this one we were okay with just integrating and not putting in absolute values, because I think this one was an always increasing function, but we didn't quite talk about that yet. Well, I'm just going to go with integrating this to get a total distance like this, and I'm going to make a statement about the difference between total distance and displacement, but for right now I'm going to go with what we did here. So the integral, so what you would do then, once you had this function, we would have this entered in our calculator, and this will be a total calculator question. I'm going to demonstrate how to use your calculator for this in some upcoming examples here. But so if we integrate from that time interval from 0 to 60 of this rate function, it's going to leave us with total distance. Okay, I'm just going to leave that one, and we're going to do more examples that are probably more applicable than that one, but that kind of demonstrate the same ideas. Okay, example 9. Okay, so this is a particle motion problem. So what I want you to understand is when you integrate something that is a rate, okay, so when you integrate a rate, it's going to equal a distance, okay, because it loses the rate. It's going to be a distance or like an amount. Like if you lose the rate. So for example, if you were integrating something that was meters per second, you'd be left with meters. If you were integrating something that was gallons per day, you'd be left with gallons. So maybe it's an amount, right? But you lose the rate. So if you integrate, you lose the rate, and that's kind of one of those little sayings that I've seen a lot of these trainings I've been to, that's one of those sayings that they always say. Tell students it's integrate to lose the rate. So it means you lose the per, second or the per hour. You lose that part of it, and you're just left with the numerator piece of that. So integrate equals, I'm just going to write this, lose the rate. Okay, so integrate to lose the rate. Okay, so here we have they're having us fill out this table, and so what we have here, this is actually a position function, right? X of t. Now here it says consider a particle moving along the x-axis where x of t is the position of the particle at time t in terms of its distance from the origin. Okay, so x prime of t, which makes sense. If I do the derivative of position, I get velocity. And it says this, where I have the absolute value, and I didn't put that on the last problem, but I want to point that out. Absolute value of your velocity, okay, and if we integrate the absolute value, so we're integrating a velocity, right? We integrate and we lose the rate, that's going to be total distance. Now there's a reason why we're putting absolute values on that, and I'll get into that. But that's the total distance that the particle has traveled in that time frame, okay, from, in this case we're going from 0 to 5. So let me elaborate on this just a little more. Okay, so right now this is a position function. We can easily find the velocity function by taking its derivative, right? So if I take the derivative of this, I've got 3t squared minus 12t plus 9. Simple derivative there. So now I've got a velocity function. So there's a position function, here's a velocity function. Okay, and it says complete the table that gives the particle's position at every 5 time intervals. So I just filled those in. This isn't super necessary to what we're going to show here, but I think they just want to demonstrate that at a certain point it was moving right, because it went from -2 to +2, but then it moved left because it went from 2 to 0. But then it kept moving left here. Now it starts moving right again. Okay, well, if we were to take a look at this this velocity function, that makes sense because it's a parabola. And remember, with velocity, if we're positive, that means it's moving to the right, and all of this part of the graph is positive until it hits an x-coordinate of 1, and then it's negative between 1 and 3 seconds. These are seconds, I think, right? Yeah. In this time interval here, now it's negative. This means it's moving left. Where I shaded in red, that it's moving left there. And now again, from time 3 to 5, now it's moving right again. Okay, and so that kind of makes sense with its position, why it was was getting further to the right. Now it started moving left. It was moving left. Now it's moving right again, and that happens right in that time frame between 1 and 3, where we see it's moving left in there. Okay, all right. So to find total distance, so when we're talking total distance, it doesn't matter if it's moving right or if it's moving left. It's just moving. We just want to total up the total amount of movement, whether it's right or whether it's left. We're going to add those together. And so to show that, with calculus and to do the formulas for it, we know that we integrate to lose the rate and get a distance, since it's, what is this, meters per second, I think. They didn't really give us any units, I guess. But we know that this is position. We could make up some units. I think we could say if the time was in seconds and the position was in meters or something, our rate would be meters per second. That would be our velocity. Now, if we don't care that these are negative values, and we worry about the absolute value of that function, really what that graph does, it takes this part of the parabola and it just flips it up like this. And so now when I do this area under here, or when I integrate it, I don't have these negative values that are taking, that I have to subtract out. So it would be all, positive. I've shaded those in green where it was positive. Okay, so if I were to, put this velocity in absolute values, now that gives me the total distance. It doesn't matter if it's moving right or if it's moving left. That'll give me just the total distance that it's traveled, from its starting position. You're just totaling the distance up. So I put that in there. Now, you can do this, on your calculator. I'm just going to quickly pull up this Calculator Pro, and I had that other function there. Let's clear that one out, and then let's put in, it was 3x squared minus 12x plus 9. So I've got 3x squared minus 12x plus 9. Okay, so there's that. I'm going to hit zoom 6 to just get a standard window. Zoom 6. Ooh, that didn't give me a good standard window. I'm going to change this, so we're going to go -10. 10. Oh shoot, I gotta clear that. 10. Clear. -10. y negative 10, y min. So we just go negative 10 to positive 10 as a typical window there. Okay, so let's graph that. Why did it do that? Oh, I forgot to put negative on this one. Negative. Hopefully that works. I'm not sure why I'm seeing not. So negative. So 3t squared minus 12t plus 9. Oh, I got a 2 there instead of a 12. 3x squared minus 12x plus 9. There we go. Okay, so now I'm seeing what that graph is. Okay, so what we're going to do with this is we're going to enter in, now since I've got it in my y equals, I'm just going to put y1 in there when I do this, but I'm going to do the integral from 0 to 5 of the absolute value of that function. Okay, and it should come to 28 when I do that. So back at the home screen, so I'm going to say math 9, and I'm going from, I'm going to clear that out. Let's try that again. Math 9 for integrate, and we're going from 0 to 5. And in here I'm going to hit alpha F4, and we're going to choose that function and that's in y1, and I'm going to hit, oh, but what I wanted to do was to put absolute values on there. So let me try this again. So absolute value, if I hit math and over to number, I can hit absolute value, which is number 1, absolute value of y1. So I'm going to go alpha F4, y1, enter. Now that's in there. I just need to get rid of this guy. Let's see, can I just delete that? These buttons are slightly different than on my calculator, so. I don't see a delete. Oh yeah, right there. Okay, delete. Okay. Let's see if this works. There, okay. So absolute value of that function from 0 to 5, it does give me 28 for that, okay? So that's how I'm going to do that. And what it's representing is this area with no negative area, like this one has the negative area. Okay. All right, so here it says y is our absolute value in this expression. So my answer to that would be, to calculate total distance, we need to consider only positive velocity. We don't care if it's moving to the left, right? It doesn't matter whether it's moving right or left. So if we're doing total distance, it doesn't matter which direction, we're just adding up those numbers, and that's what this is going to represent. Okay, so it just makes everything positive. Okay, and then in a similar way, if we wanted to find total displacement, so displacement means where does it end up, right? And so we need to consider that it's moving left here, because it put us back to a different, it moved us to the left. And so total displacement means, like, how far is it from its original starting position? Okay, so it's going to be, so that makes sense that this is a little less because we're subtracting out a little bit of area here, which takes into account that it moved left. And so, even though we want to take that into consideration, because we're talking about where is it in, respect to where it started from. And so here we don't do the absolute values, and we get 20 for that one. I'm not going to type that one in, but hopefully you can take my word on that one. Okay, so this is, I think, the last example I'm going to run through. And this wasn't a problem that was on the AP exam from 2014. It's a good one to run through here. And it does demonstrate well the second fundamental theorem of calculus. Okay, so with this example, we have one of these, just some lines, right, where it was easy enough to calculate some areas, and I did that. An area of 2, this area in this triangle, it was like 5 by 4, so that would be 10 for that, because we take half of that. And then I stopped here because one of the questions it has us go to 3, I believe. So that ended up being 1 by 2, so that was a 1 or a negative 1 since it was below the x-axis. Okay. So it says the function f is defined on the closed interval from -5 to 4, and it consists of those line segments up above. Let g be the function so g is defined as an antiderivative of f, okay? So this is a common problem they like to set up, because then they start asking you questions about g prime, and g prime is going to be using the second fundamental theorem, which is basically just going to be then f of x. And keep in mind, what they're showing you here is the graph of f. So if you're going to answer any questions about g prime, or the first derivative of g, you're actually looking at function values on f up here, okay? All right, so right here, first now it's just asking us to find g of 3. So g of 3 means, okay, that means g of 3, I got to put a 3 into this function for any x, and that 3 is actually going to be on the top bound then here. So it goes from negative 3 to positive 3, right? So I'm finding the area from negative 3 to positive 3 of this, under this f function, right? And so hopefully I did this right. So from negative 3 to 2 was 10, but then if I go, now I have to take this one away, right? So for my total area, it'd be 10 plus negative 1, so I would get 9 for that one. Okay. Part B, it says, on what open intervals contained in the interval from negative 5 to 4 is the graph both increasing and concave up? Okay, so now we got to go back and remember, okay, what does increasing mean in terms of a function and derivatives? Okay, so increasing means that the first derivative is positive, right? G prime would have to be positive, which would indicate that g is increasing, right? And to be concave up, the second derivative would have to be positive, okay? So the second derivative of g would have to be positive, which means that the first derivative would be increasing, okay? So that would be a couple things to consider. So what I want to point out here, okay, so since g of x is the antiderivative of f, then g prime would have to then be, just by first fundamental theorem, that would be f of x. So g prime is equal to f of x. So what do we know from that information? Okay, we're asking about increasing. So g, where is g going to be increasing? Wherever g prime or f of x is positive, right? So g prime would be increasing when, or I'm sorry, g would be increasing when g prime is positive. And since g prime is equal to f of x, we want to look up above and see where is f of x positive. That's part of it, okay? So we know f of x is positive in this area here, not this stuff. So this is automatically eliminated, okay? But now we need to think about also being concave up. Okay, so concave up means where is the second derivative of g going to be positive? Now the second derivative of g is equal to the first derivative of f. First derivative of f would be where is this, where is it increasing? Because wherever the function's increasing, that means the first derivative is positive, right? So g is concave up. That's supposed to say g, it looks like a. So g is concave up when the second derivative of g, which is equal to the first derivative of f, is positive, or when f up above is increasing. Where is f increasing? So we want to see where is f increasing and also where is f positive. So those two restrictions, that is just this section right here. Where is f increasing and where is f positive? And that's from negative 3 to 0. Okay, so that's what I put for my interval for that answer. That's from negative 3 to 0. So we want it both increasing, where f is positive, and where f is increasing. And that's all based on the relationship here of the derivative of g being equal to f and the second derivative of g being equal to the derivative of f. Okay? Okay, and then this last one, this is, again, these are kind of common types of problems here. They define a new function, but it has g in it. Okay, and they say h of x is defined here. And they want us to find h prime of 3. So they want us to find the derivative and then plug in a 3. So in this, because this is a quotient, we have to use the quotient rule for derivatives, right? So h prime of x, and remember quotient rule, you all remember that little song, low, d high, so low is 5x, d high is going to be g prime then, derivative of high, minus high, d low, so the derivative of the 5x is 5, and then all over the square of what's below, so all over 5x squared. So I've got 25x squared down there. Okay, so that's in general, that's my derivative. Now I want to do h prime of 3, because that's what it's asking for. So everywhere I have an x, I'm going to put a 3. So that's 5 times 3, and then times g prime of 3, minus g of 3, and then just times 5. And then underneath I've got 25 times 3 squared. Okay? Now, we got to go back and find what some of these values are. Well, that's just 15, but g prime of 3, okay? G prime of 3. So I kind of wrote out a connection here. G prime of 3, remember the derivative of g is the same as f. So since g prime of x equals f of x, that means g prime of 3 means f of 3. Now, up on the graph, what is f of 3? It's just the function value at 3. So f of 3 right here, that y-coordinate is negative 2, okay? That y-coordinate's negative 2. So that's the value right there, negative 2. So g prime of 3, which is the same as f of 3, is equal to negative 2. So I'm replacing that with negative 2, 15 times negative 2. And then minus, and I've got g of 3. Now that's one I already calculated, g of 3. That's usually the way they ask these on these AP. They're like, use the answer you had already up here. So that's 9. So I'm going to replace that with 9. Now let's just say you got this answer wrong, and you substituted the wrong answer in here. If you did all this work right, they would still count it correct. You would just lose points on getting this one wrong, but not this one down here. But anyway, so g of 3, which was 9, and then times 5, and then I'm just going to simplify that. That's negative 30 minus 45 divided by, so it ends up being like negative 75 over 225 and simplifies down to negative 3/7. Okay, so that's it. I know I went through this kind of fast, but we'll do it in class as well. This is an optional example. This one takes quite a while, so we're gonna hold off on that one for now. Okay, so that's it for this